we finally come to the existence and uniqueness theorem for solution to a differential equation. So consider x dot is equal to f of x. Consider this differential equation where f is a map from Rn to Rn, and consider the point x naught in Rn. Assume f is locally Lipschitz at x naught, then there is a delta greater than 0 such that there is a unique solution x of t to the differential equation x dot is equal to f of x with the initial condition x0 equal to x naught. So such a unique solution exists for the time interval t belonging to 0 to delta. So there is some number delta that is strictly positive, because of which there is this interval of time 0 to delta for which we have a solution, and moreover the solution is unique. That is what it says, with the initial condition x0 is equal to the point x naught where the function f was assumed to be locally Lipschitz. So it turns out that existence and uniqueness of a solution is being guaranteed for only an interval of time. It is possible that this interval of time is very small, but it is guaranteed to be a non-zero interval of time. It is not just one point, but it is an interval 0 to delta. We can ask the question, is locally Lipschitz important? After all, we have spent analyzing the significance of Lipschitz, locally Lipschitz, its relation to differentiability and continuity. We could ask, is this locally Lipschitz property really crucial for the existence and uniqueness of a solution to the differential equation? For this purpose, we will see that the differential equation x dot is equal to x to the power 1 by 3 has at least two solutions. Why? Because x to the power 1 by 3 turned out to not be locally Lipschitz, and hence uniqueness was not guaranteed by this theorem, and we will see that there are two solutions. So what are these solutions? This is what we will see now. So consider this differential equation x dot is equal to x to the power 1 by 3. So we can rewrite this as x to the power minus 1 by 3 dx equal to dt, and upon integrating both sides we see that we get this equality where c1 is some constant, and rewriting these terms x to the power 2 by 3 is now equal to 2t by 3 plus c0. So c0 and c1 are related by the constant 2 by 3. For convenience, we have renamed c1 times 2 by 3 as c0. Then upon taking suitable powers, we see that x of t is equal to 2t by 3 plus c0 raised to the power 3 by 2. So we see that this is also a solution to the differential equation. And how do we calculate c0? We can ask the question, suppose at t equal to 0, the differential equation was at 0, x satisfied x0 is equal to 0 at t equal to 0. By substituting this, we can get c0. So we see that x of t equal to 2t by 3 to the power 3 by 2 is a solution to the differential equation. Which differential equation? X dot is equal to x to the power 1 by 3 with the initial condition x0 is equal to 0. But is this the only solution? No, because if x dot equal to 0 at x equal to 0, then we also know that x of t is also a solution. Is also a solution of the differential equation. So we see that if x is equal to 0 at t equal to 0, then x dot is equal to 0. Why is x dot equal to 0? Because we put x equal to 0 here, and cube root of 0 is nothing but 0, and hence x dot is equal to 0. And then we conclude that x is equal to 0 for all time t. This is one solution to the differential equation, but we see that xt is equal to 2t by 3 whole to the power 3 by 2 is also a solution to the differential equation with the same initial condition. So for the same initial condition, we see that we have two solutions to the differential equation. Let us just draw a graph of x versus time. So, here is this x that was 0 until t equal to 0, and from here it is growing as 2 by 3 to the power 3 by 2 times t to the power 3 by 2. This is a graph of x versus time t, and in addition the differential equation also has equivalently equal to 0 as a solution to the differential equation. In other words, at this point t equal to 0, there is this solution that comes out of x equal to 0, and it also continues at x equal to 0 as has another solution. At this point the vector field, we see that it is pointed, sorry, this is something we have to plot like this. So, the graph of x to the power 1 by 3 is like this. We see that of course there is this instability, but at x equal to 0 itself the arrow had length 0, because the graph of f crossed the x axis at x equal to 0, and hence if it is at the point x equal to 0, then it continues to be at the point x equal to 0. This is what our vector field diagram told us. But here we see that in addition to continuing to be at 0, there is also this possibility that it comes out, it emanates out of the equilibrium point without requiring a perturbation. While this figure says that this equilibrium point is an unstable equilibrium point, we see that upon perturbation there are points that are trajectories that are going away from the equilibrium point. But here is an example, because of this non-locally Lipschitz property at the point x equal to 0, without a perturbation also we see that there is a solution that emanates out of the equilibrium point, thus making us ask what exactly is the definition of an equilibrium point, when there are solutions that can emanate out of the equilibrium point even without requiring a perturbation. For these purposes, we will from now on eventually assume that a function f, when studying a differential equation, satisfies locally Lipschitz at every point x naught. But this is an example where without locally Lipschitz property, it turns out that there can be non-uniqueness of solutions to the differential equation. So, we see that the solution x is differentiable. We were able to get explicitly the solution x as a function of time. We can also differentiate this as a function of time and see that it solves this differential equation. F of x is continuous, but it is not locally Lipschitz at x equal to 0. That is why the previous theorem would not guarantee existence of solutions, existence and uniqueness of solutions, and here is an example where uniqueness fails. Okay, so because of the importance of this result of existence and uniqueness of solutions to differential equation under locally Lipschitz property, we will, because of its importance, we will see the proof. So, the outline of the proof will be as follows. We will define an operator P that takes one estimate of the solution trajectory and gives a better estimate of the solution. So, this operator P takes a trajectory which is a solution to the differential equation on the interval 0 to delta, and it gives a better estimate of the solution. So, this is going to be called Picard's iteration because of Picard's work in this area. So, P x n is an estimate of the solution trajectory at the nth iteration. We will define P such that the desired solution will satisfy Px equal to x. In other words, x will be a so called fixed point. Why do we call it fixed? Because the desired solution, the solution to the differential equation, takes x and gives back the same x. In other words, while it takes different xn and gives back xn plus 1, possibly xn plus 1 is different from xn. While this is possible in general, we will construct P such that the desired solution x will satisfy Px equal to x. In other words, P fixes x. So the Lipschitz condition on f will help to prove convergence of this iteration, convergence of this iteration to a unique fixed point. But this fixed point would be unique provided we are looking for a so called complete space. These are some things that we will define precisely. So for this purpose we will use a so called Banach fixed point theorem. So please note that the point in this context is a trajectory x of t for the interval 0 to delta. Possibly the interval 0 to delta is a very small interval. In other words, delta is only slightly more than 0, but it is positive, which means that the interval is not just a point, but it is an interval of time of length delta. So how will we define this Picard's iterates? So define the operator P that takes a continuous function x of t and gives another continuous function y is equal to p of x. How will we define it? Px is again a function of time. Px at any time t is defined as x naught plus the integral from 0 to t of f of x tau d tau, where t belongs to the interval 0 to delta. So t comes in here and this integral is being added to 0. So we see that for this t equal to 0, this particular trajectory is also equal to x naught. So these are different functions of time that start from x naught. So what is the significance of this operator P with our solution to with our differential equation? We see that xt is a solution to the differential equation d by dt of x is equal to f of x with this initial condition x0 is equal to x naught if and only if xt is a solution to the integral equation, to this integral equation x of t equal to x naught plus integral from 0 to t f of x tau d tau. So by differentiating this right hand side, this is something we can quickly check. Y is solution to this integral equation, also solution to the differential equation. We see that x appears on both sides. Here is x and x is also inside this integral. So d by dt of x is equal to derivative of this is equal to 0, and since t appears only here, this is nothing but f evaluated at the end point. So this is what our differential equation was. In other words, a solution to the integral equation is exactly a solution to this differential equation also. When we integrate this on both sides, we see that x of t also satisfies this initial condition plus integral from 0 to t of the right hand side. In other words, solution to the differential equation, when integrating both sides this differential equation, we obtain exactly the integral equation. Thus, solution to the integral equation is a solution to the differential equation, and solution to the differential equation is also a solution to the integral equation. However, we see that here also x appears on both sides and here also x appears on both sides, and it is not clear that going from a differential equation to the integral equation is genuinely a improvement. We will see that obtaining an integral equation allows us to use Picard's iteration. So the latter, what is important is that when x satisfies this integral equation, that x is also a fixed point of this operator P. Why? Because the right hand side is nothing but P of x, and what x we have put in here is exactly what is also here. That is why this particular integral equation says that P of x equal to x. So we will first see the special case when f is independent of x. Maybe f is allowed to depend on time. Only here we will assume that f is a function of time explicitly and there is no dependence on x. So consider this differential equation, d by dt of x is equal to f of t with this initial condition x naught. So there is no dependence of f on x. Then we are able to integrate this x of t, we can then define as x naught plus this integral from 0 to t of f of tau d tau. So there is no guess or iteration required to define this. Yeah, such a definition x will always satisfy this differential equation. But when f depends on x, then we are not able to define this. Why? Because x appears both on the right hand side and left hand side of this integral equation. So the word define can no longer be used here. So only a carefully chosen x will satisfy this equation, and that is indeed the solution to our integral equation. So what we will do now is, we will take x1 as some function of time. It turns out that within a small neighborhood of the actual solution, which solution we take will not matter. So we will take x1 of t equivalently equal to x naught. So we will take the function x1 which is always equal to x naught value. X naught is a point in Rn which corresponds to our initial condition. There is one particular function which is always equal to x naught for all time t, that we will take as our initial x1. Then we will define x2 as x naught plus this integral with f evaluated at x1 instead of x2. So now since we have x1 here which we know and x2 which we do not know, we are allowed to use x2 defined by this right hand side. In other words, x2 is equal to p times x1. So we can similarly define x3 as p times x2, and in general xn plus 1 as p times xn. So the question arises, will this converge? Will this converge to a solution? In other words, will it converge to a fixed point of the operator p? So the answer is, it will converge for a carefully constructed delta that will be strictly greater than 0, and for ensuring that this delta is strictly greater than 0 and that it exists, we will be using the Lipschitz, locally Lipschitz property of f at the point x naught. So this is the hard and remaining part of the proof which we will proceed and do now. So please note that x naught is a point in Rn. This is the initial condition for the differential equation d by dt of x is equal to f of x. On the other hand, x1, x2 up to xn are continuous functions of time, and these are iterates of the operator p. These are no longer points in Rn, but they are functions which take their values in Rn for different time instance.